Hi everyone, welcome to lecture 33 of your circuit class. And lecture 33 is about complex power. So the objectives of this lecture, the first objective is to define and determine complex power. And the second objective is to know that each circuit has a power balance, which means that the summation of power supplied is equal to the summation of power absorbed. As in DC circuit, however, we have to deal with the circuit as in AC. So we will start with complex power. So complex power is a complex number that contains all the power information and it is measured in volt ampere, the same unit as the apparent power. And now you will know the reason. So our complex power, which is a complex value, that's why we have a tilde at the top of it, while in your textbook that you will have a bold letter, that is equal to P plus or minus JQ, where P in this equation is the average power, which is the real part of the complex power. And that is in watts. So our P is equal to VRMS, IRMS, and these are magnitudes, multiplied by cosine of theta V minus theta I, and that is in watts. The Q is the reactive power, which is the imaginary part of the complex power in volt ampere reactive. So that means our Q is equal to VRMS IRMS sine of theta V minus theta I, and that is volt ampere reactive. So that means our complex power can be written as complex S is equal to VRMS IRMS cosine of theta V minus theta I plus or minus J VRMS IRMS sine of theta V minus theta I. And this is equal to VRMS IRMS, which can be taken as a common factor, multiplied by cosine of theta V minus theta I plus or minus J sine of theta V minus theta I. So that is in rectangular form, and that is of course in volt ampere. So if you look at this, that is a rectangular form since we have a J involved. So in polar form, the complex power is complex S, which is phasor S, that is equal to VRMS IRMS then theta V minus theta I, and that is in volt ampere. So this is the form in polar form. Of course that we can use the complex power, let's say in terms of phasors, and over here that values are not RMS, we can say that our S is equal to 1/2 V times I conjugate. Why is that? Because you remember that when we have our, let's say, phasor V is equal to Vm with angle theta V, and phasor I is equal to Im with angle, let's say, theta I. So when we have our angle to be theta V minus theta I, right? So this is 1/2 Vm with angle theta V times Im with angle, originally is theta I, but since over here it became negative, then we have to take that as a negative, which means this over here is Im with angle theta I, but that is conjugate, you see, because we flipped the sign. So this is equal to, as if we are using our RMS values, so VRMS times IRMS conjugate, and that is in volt ampere. You see this formula here? That is the most powerful formula in AC circuits. The reason behind that it contains all the power information. Let's say why really we said that the most powerful formula in AC circuits. Because let's say that the complex power in terms of load impedance ZL. What we can do. So our ZL is equal to phasor V over phasor I. And the same thing, that is, let's say, VRMS phasor divided by IRMS phasor. And this is equal to VRMS with angle theta V divided by IRMS with angle theta I. So if you look at this here, we can write that as VRMS with angle theta V divided by IRMS. However, this theta V, theta I mean, when we bring it to the top, we have to flip the sign. So minus theta I. So that means our ZL is equal to VRMS over IRMS with angle theta V minus theta I. So if you look at this, the theta V minus theta I for the load impedance, it is the same as the angle for the complex power for that, let's say, load, theta V minus theta I. Okay, so now that is in ohm. So this will give us that our VRMS is equal to the load impedance times IRMS. So our S in this case, that is equal to IRMS squared times ZL, which is equal to VRMS squared over ZL conjugate, and that is in volt ampere. So if we have the current, the RMS current is known, to find the complex power of a load impedance, you will just multiply the RMS current squared multiplied by ZL. If you look at IRMS here, that is not a phasor quantity. You just take the magnitude of that current and you square it and multiply it by the load impedance. If we know the voltage across the impedance, then that VRMS, which is the magnitude of the phasor RMS squared divided by ZL conjugate, it will give us our complex power S in volt ampere. So based on that, we can say that we do have the power triangle as mentioned earlier. So this is our P, this is our Q, and this is our S, which is the apparent power. So from this we can say, and this is of course our theta, which is theta V minus theta I. So in this case we can say our S squared is equal to P squared plus Q squared. And we can say also cosine theta, and this is the power factor, right? Power factor. That is equal to P divided by S. Of course that this is a right triangle. That's why we are getting these, let's say, equations. Sine theta is equal to Q over S, and then we have also tangent theta, that is equal to Q over P. So as long as we know two quantities in the triangle, we will be able to find the other two values. So conservation of AC power for any given circuit there must be a power balance. That is power absorbed is equal to power supplied, like as in DC circuit. However, in AC circuit we have many types of power here. So in this case, average power supplied equals to average power absorbed, which means that the summation of P supplied is equal to the summation of P absorbed. The second thing, that the reactive power supplied is equal to reactive power absorbed. So that means summation of a Q supplied is equal to the summation of a Q absorbed. And the last thing, that complex power supplied should equal to complex power absorbed, which is summation of S supplied is equal to summation of S absorbed. So let us go over an example to show, let's say, the application of these formulas. So we will have over here our example. And the example is saying that a power utility company generated a 100 kilowatts to supply a load through a transmission line. The load draws 240 ampere RMS if the load voltage is 460 volts RMS and the power factor of the load is 0.9 lagging. Find the losses in the transmission line. Solution. So the meaning of this, we can put that as a circuit. So we have our source here. So this source is going to supply this load, and this is our transmission line. So we can say that our P supplied is equal to 100. If you look at that, we said 100 kilowatt. So that is 100,000 watts. Our VRMS for the load, that is equal to 460 volts. We have the power factor of the load, that is equal to 0.9 lagging. We have IRMS of the load, that is equal to 240 ampere. Since we know that P supplied should equal to P absorbed, so the P supplied is equal to the P line plus the P load, because as you can see that this here is supplying, this is absorbing, and this is absorbing. So first we will get our P load. Our P load is equal to VRMS of the load times IRMS of the load multiplied by cosine of theta V minus theta I, and that is equal to VRMS load times IRMS load times this over here, cosine theta V minus theta I. We said that is our power factor, and our power factor is given over here, which is 0.9 lagging. So that means this is our power factor of the load. So we will just substitute VRMS load, that is 460, IRMS load, that is 240, and the power factor is 0.9, and that is equal to 99,360 watts. So therefore, since we know that P supplied is equal to P line plus P load, so P supplied is 100,000, P line we don't know, and P load is the P load is 99,360. So from that we can find our P line, and that is 100,000 minus 99,360. So the line has a loss of 640 watts, and this is the power loss in the transmission line. Let us go over another example here. And the example is asking us to find the input source voltage and the power factor of the source for this circuit here. So the circuit, we have a voltage source here that is called Vs, a resistance, inductive reactance. Then we have over here a load connected, and that load takes 12 kilowatts at 0.87 power factor lagging. Then we have another transmission line here of a resistance and inductive reactance, and then we have another load connected over here, and this load is absorbing 24 kilowatts, 0.9 power factor lagging. The voltage across this load, we call it, let's say, VL, that is 240 with angle 0 volts, and that is given in RMS. The value over here is 0.03, and this is J 0.1 ohm. And over here we have 0.1 and J 0.3 ohm. So we are saying that in the question, find the input source voltage. That means I need to find this Vs from this circuit. And the second thing that, and find also what the power factor of the source. So we need the power factor of this source here. The power factor, we will be able to find it under the condition that Vs is known and the current flowing through that source is known. So if I call this current here to be Is, then I will have over here a current called I1 and a current over here called I2. And then Is is equal to I1 plus I2. So now, our solution here, we will start with Vs. Vs is equal to VL plus I2 multiplied by 0.03 plus J 0.1 plus Is multiplied by 0.1 plus J 0.3. Let me explain this. So I need this Vs here. So what we are saying that if I go with, let's say, this loop here, I will be able to find that. So our Vs is equal to the voltage drop here, and that is Is times 0.1 plus J 0.3. Then the voltage drop over here, which is 0.03 plus J 0.1 times I2, plus this voltage over here. That is our node. So negative Vs plus 0.1 plus J 0.3 Is plus 0.03 plus J 0.1 I2 plus VL is equal to 0. Where Is is equal to I1 plus I2, and all of these are phasor quantities. So now to get, let's say, our I2, we do have over here 24 kilowatts, and we know the power factor, and of course that we know the voltage for that load. Then we can say if this over here, I call it, since that is I1, I call this as load 1 and I call this as load 2. Then I can say P2 is equal to VL I2 times cosine theta V minus theta I, and that is power factor 2. So from that, the only unknown is I2. So our I2 is equal to P2 divided by VL PF2, and that is equal to 24,000 divided by VL is 240, and the power factor is 0.9, and that is equal to 111.11 ampere, and that is in RMS, since the voltage is given in RMS. So now PF2 is lagging, so that gives us PF2 is equal to 0.9 lagging. So we know PF2 is cosine theta is equal to 0.9. To find this theta, that is the inverse cosine of 0.9. And that is the inverse cosine of 0.9 is 25.84 degrees. And since it is lagging, we are gonna put over here the angle to be negative. So from that, we can say our I2, because if you look at this here, that is just the magnitude. So the phasor is 111.11 with an angle of negative 25.84 degrees. And that is ampere RMS. Why we took the whole power factor to be associated with the current in this case? Because our angle for the voltage is 0. So we took the whole thing here for the current. But that 0.9 power factor lagging, which is the cosine of the angle difference between voltage and current, okay? So the angle of the voltage, which is 0, minus the angle of the current, which is negative 25.84, that will make our power factor to be 0.9 lagging. So that is our I2. So now we can say, since we have our I2 is known now, which is the current flowing here, then now I can find, let's say, the voltage across this load, which is from this point to this point. If I call that as V1, because that is the voltage across this load, then V1, we can take this loop to find it, right? This loop. So that means I will have V1 or negative V1 plus 0.03 plus J.1 times I2 plus VL, which is 240 with angle 0, is equal to 0. That means really our V1 in this case here is equal to the voltage drop here plus that VL. So V1 is equal to VL plus 0.03 plus J.1 times I2. And we will just substitute. That is 240 with angle 0 plus 0.03 plus j 0.1 times 111.11 with angle negative 25.84 degrees. And the answer here is 247.99 with angle 1.98 degrees, and that is volts in RMS. Now, to find I1, first we can go with P1. P1, we are saying that is equal to V1 I1 power factor 1, because power factor 1 is cosine of theta V minus theta I. So from this, the only unknown is I1, and that is P1 over V1 PF1. And P1, it is 12,000 divided by V1, we just found it, which is 247.99, and our power factor 1 is 0.87. And the answer here is 55.62 ampere, and that is in RMS, since all of our calculation in RMS. So now our power factor 1 is equal to cosine of theta V minus theta I. So this is V1 and I1, and that is equal to 0.87. So from that we can say theta V1 minus theta I1 is equal to the inverse cosine of 0.87. And the inverse cosine of 0.87, that is equal to 29.54 degrees. So from that we can say our theta I1, because it is unknown, is equal to 29.54 degrees, right? Or theta I1 is equal to theta V1 minus 29.54 degrees. This is what I meant. So theta I1 is equal to theta V1 came out to be 1.98 degrees, and that is from here. See, that is the angle of V1. 1.98 degrees minus 29.54 degrees, then we will get our angle to be negative 27.56 degrees, and that is the angle for the current I1. So from that we can get our phasor quantity for current 1, which is equal to, the magnitude came out to be 55.62, and then with an angle of negative 27.56 degrees, and that is in ampere RMS. So now we can get our IS. IS is equal to I1 plus I2, and both the quantities are known. So I1 is 55.62 with angle negative 27.56, and I2 came out to be 111.11 with an angle of negative 25.84 degrees. And our total here is 166.71 with an angle of negative 26.41 degrees, ampere RMS. So now we know IS, so we can find our VS. VS is equal to, substitute in the equation that we wrote at the beginning, which is this equation here. So our VS is equal to the VL is 240 with angle 0 plus 0.03 plus J 0.1 times 111.11 with angle negative 25.84 plus 0.1 plus J 0.3 multiplied by the current, which is IS, that is 166.71 with angle negative 26.41 degrees. And our VS came out to be 288.16 with angle 8.48 degrees, and that is volts in RMS. So now this is our VS, the first requirement, which is the value of the voltage source. And now we need the power factor of the source. So power factor of the source that is equal to cosine of theta V of the source minus theta I of the source. And that is equal to cosine of theta V of the source is this value here, which is 8.48 degrees, minus theta IS. If you look at this, this is our IS, so this is our angle for IS, negative 26.41, negative 26.41. And that is equal to 0.82. And now we look at the voltage. If you look at the voltage, that is positive 8.48 and the current is negative 26.41. Then the current is behind. That means our power factor is lagging. And this is the final answer in this case. Based on that, we can say, or you have to pay attention to our complex power. So our complex power can be expressed as whether that you can say the S is equal to 1/2 VI conjugate, that is equal to the phasor VRMS times the conjugate of the RMS current, or we can say that is equal to P plus J plus or minus JQ. So when we are saying that, that means it is really P plus JQ if it is inductive load, okay, or P minus JQ if it is a capacitive load. And always the complex power angle and load impedance angle are equal. So if I have, for example, our S of the load to be, let's say, 10 with angle 30 degrees, then we can say for sure the angle of the load impedance have to be ZL with angle 30 degrees. So this angle and this angle are equal all the time. And of course that we can say our complex power, if you look at this here as what we said, VRMS times IRMS conjugate, and we have said that this formula is the most powerful formula in AC circuit. Why is that? Let's say that if the VRMS and IRMS are known, then we can use this formula. So VRMS is known, IRMS is known, then VRMS times IRMS conjugate is equal to the complex power. Now, if VRMS and ZL are known, then we can substitute S is equal to VRMS is known times IRMS is not known, however ZL is known. So IRMS is equal to VRMS over ZL. However, that the whole thing here, that is conjugate to substitute for that current. So VRMS times VRMS conjugate, that will be VRMS squared divided by ZL conjugate. And the third one, if IRMS and ZL are known, then our S is equal to VRMS IRMS conjugate. So in this case, VRMS is not known, but IRMS is known. So VRMS is equal to ZL times IRMS. That is VRMS times IRMS conjugate. So if you look at that, we have our IRMS times IRMS conjugate, that is IRMS squared multiplied by ZL, and that is the complex power. If you understand this, that is really great, and you will be in good shape for this lecture. And over here is our homework problems for this lecture. Thank you for watching.